crucial moment for climate action. To stabilise the climate, we must stop using fossil fuels in our cars and homes. Chemistry is electrifying society's transition to net zero, powering new innovations in batteries and energy storage. Scarce elements at the heart of these technologies must be sustainably sourced, used and reused. Get involved. Sustainability. Powered by chemistry.
Hello everyone, and welcome to the Royal Society of Chemistry's live event discussing the role, production and use of hydrogen as a low-carbon energy store and chemical feedstock. This has been timed to coincide with COP27's energy-themed day. My name is John Broderick and I'm the Net Zero Programme Manager at the RSC, helping us to reach net zero greenhouse gas emissions by 2040 and sharing the work from the chemical science community with policymakers and other stakeholders. I'm really pleased to be talking about low-carbon hydrogen today, as it will have an increasingly important role to play in our energy and chemical industries. To stabilise the climate, we need to reach a balance of sources and sinks of CO2 that's usually termed net zero. That means all sectors must get very close to zero emissions, not just the relatively easy ones like cars, heating and cooling that can take energy directly from renewable electricity. I believe hydrogen will have a global importance because of its diversity of uses, from fuel for aircraft and ships to molecular energy storage and fertiliser for growing crops. Much of the vital work to deliver this is being done by the chemical science community, whose contribution we'll highlight today. So, in the next hour, we'll hear from 5 different researchers from around the world about their work. We'll also find out a bit more about the new RSC Open Access Journal, EES Catalysis, which is clearly very relevant to us all talking about energy conversion to chemical bonds in molecules. And we'll be sharing details of a special collection of freely available open access articles across the range of RSC publications, which you can access from the QR code on screen now. This webinar is being recorded, so you can watch back at a later date or share with colleagues. And as we're live on social media, you can join the conversation and ask questions, which we'll try to work into the programme. But first of all, I'm pleased to welcome Jonathan Oxley, Director of the CBI Humber Cluster and Royal Society of Chemistry Trustee. Jonathan, great to have you with us today. Could you introduce yourself and your role at the CBI?
Brilliant, thank you, John, and it's great to be here joining you all in this discussion whilst COP26 is front and foremost in the agenda to do with energy, of course. So my name is Jonathan Oxley. I am the CBI's Director of the Humber Cluster. This is an initiative by the CBI to, rather than just talk about what businesses should be doing, actually join them on that journey. And what we're doing here in the Humber is about bringing businesses together to help decarbonise the industry and develop cleaner, greener products that are better for people, place and planet here in the Humber.
Great, thanks, Jonathan. So briefly, before we get into discussing the Humber Cluster, can you tell us a bit about why you think low-carbon hydrogen will be so important in tackling climate change? What motivates you? What are the drivers for the CBI working on this issue?
Sure. I mean, the CBI are helping other businesses work on a whole variety of the different tools we'll need to get to net zero, and hydrogen is certainly recognised as one of those tools, John. I think we're going to need an increasing number of different tools to deploy in our race to get to net zero. And whilst one of the obvious things we should think about is using less energy efficiency, we should think about electrification and resource efficiency in all its different ways. I think we are increasingly going to have to also look at options such as hydrogen, where we might need to effectively to find other fuels that we can use other than electrification for processes that aren't really suitable, perhaps, or aren't so suitable for electrification. So that's why we're supporting businesses in the Humber who are working on a whole variety of different hydrogen projects.
So there's a lot of different projects going on in the Humber, from energy generation to hydrogen production, hydrogen distribution, storage, consumption. Can you tell me a bit more about that range and the partners that are involved?
Sure, absolutely. So you're right. I mean, it's not for no good reason that the Humber is known as the UK's energy estuary. There's an awful lot of activity going on in this area, in that space of energy production, but also energy consuming businesses. We're home to 2 of the last 6 refineries in the UK, for example. We've got one of the last 2 steel making production facilities here in the Humber, and a whole variety of other different operations that are reliant to varying degrees upon hydrogen. Upon energy, and also upon other molecules in terms of production processes. So the hydrogen element, we see a number of different opportunities here. The Humber is effectively has access to around 80% of the licensed CO2 storage areas that have so far been released by the government. So we've got a ready avenue effectively for storing our CO2 just off the coast of the Humber. And what that allows us to do is to think about creative ways and different ways in which we can deliver lower carbon energy. One of those vectors, of course, being hydrogen. We're also home to around 25% of the UK's wind power, which comes onshore, and the world's largest wind farm. So we've got access to very low carbon and relatively cheap electricity, which we can think about deploying in terms of things like electrolysis for green hydrogen production. So we've got a number of different components of the sort of moving jigsaw puzzle that allow us to think about how we can, first of all, produce the hydrogen, but we're also home to some assets that we can use for the storage of hydrogen. And therefore you can start to think about things like interseasonal storage perhaps, or certainly storage that extends beyond hours and perhaps even a few days that battery storage might offer. You have another vector to store energy, perhaps it's a hydrogen molecule, for example. So those are some of the key elements we've got. Some of the partners that are active in this space, it's actually probably easier to list the partners who are not active in this space in the Humber. We have British Steel looking at hydrogen for their steel production. We've got Centrica involved in the storage aspect, Associated British Ports and Air Products looking at hydrogen production through green ammonia importation, etc. We've got Drax looking at potential for hydrogen production through biomass coupled with carbon capture and storage. Colleagues at Phillips 66 who are well used to using hydrogen in a refining production process, obviously, but now looking at how they might use hydrogen as a fuel, for example. So we've got a lot of different actors and companies around the Humber who are all actively exploring how they can best use hydrogen in pursuit of a low carbon net zero business agenda in the Humber.
So Jonathan, it sounds fantastic. There's so much there. Are there advantages to it being a cluster and all of those projects being co-located? And why the Humber geographically? I mean, you've mentioned all of the industry that's there already. What other advantages does that location have?
Yeah, sure. I mean, the Humber has a long history of trading and manufacture, going right back to, the 1700s when the first sort of port traffic was recorded back in history. And indeed, it's even had hydrogen in the Humber quite some time ago. I think it was 1921. There was the untimely demise of a hydrogen-powered airship in the Humber, believe it or not, which is perhaps not the example we want to focus on today, but it gives you an illustration that this region is not unfamiliar with hydrogen and the use of hydrogen as a fuel or a transport medium, for example. So the reality is here in the Humber, not only do we have all these different businesses who are dependent upon using a fuel, could be hydrogen, for example, in this instance, producing a fuel, again, it could be hydrogen as we're talking about today, but we also have the sort of infrastructure that supports that sort of energy deployment and energy use in the Humber area. And behind that, of course, we've got an experienced set of professionals and technicians and technologists who are used to dealing with flammable materials, operating process equipment. We've got the sort of training providers in this area. We've got a number of key training providers, Catch Training College on the South Bank. We've got a number of others too. And we've got supply chain who are used to supplying the sorts of materials that are needed in order to support these sort of industries. And that all coming together in the Humber is effectively what the notion of a cluster is.
That's great. And you mentioned infrastructure that goes there and about access to the CO2 storage in the North Sea. That brings us to think a little bit about CCS, carbon capture and storage, and how that relates to hydrogen. Could you tell us a little bit about that connection and the importance of that carbon storage?
Yeah, sure. I mean, so obviously we have industries in this region that are producing quite a lot of CO2. In fact, the Humber Cluster is the largest industrial cluster in the UK by virtue of CO2 emissions, around about 20 million tonnes a year of fossil-derived CO2. And if we want to capitalise on things like the potential for negative emissions that you can get by coupling biomass with carbon capture and storage, we're actually looking at scaling that up to anywhere near 36 to 40 million tonnes. And that's before also we think about potentially offering other businesses the opportunity to come and locate in the Humber to get their operations to net zero. So having carbon capture and storage availability on our doorstep effectively is a very helpful thing. From the point of view of hydrogen, of course, whilst there is a lot of attention on the production of green hydrogen through electrolysis of water, which is fantastic and definitely needs to be scaled up, we also face the challenge of how we get to significant levels of hydrogen production when we're looking at heavy hydrogen consumers like blast furnaces and such like. And we're not going to get there as quickly as we need simply on the back of green hydrogen production through electrolysis of water. And this is, of course, where blue hydrogen can come in. And this is about taking methane gas and undertaking the steam methane reformation, but then capturing the CO2 and making sure we store that just as we would in any other CO2 producing process. And what that allows us to do, if it's done well, is to generate very low carbon levels of hydrogen, aka blue hydrogen, that can then be used to scale in other areas and other applications rather, where it needs to be used in significant quantities.
So there are some voices that would say that blue hydrogen isn't compatible with net zero because of the fossil fuel element, like you say, the methane that's required for it. And indeed, there's a paper in our collection that assesses the life cycle impacts, showing that there's higher emissions than green hydrogen from electrolysis, but it's still potentially low carbon, very much lower than the way hydrogen is produced at the moment. Yeah, you think it's important because of that opportunity to scale and the potential pace of delivery?
I think both of those aspects are particularly important, yes. And when you think about when you think about where we are in terms of the energy transition, we are quite close to the beginning of the energy transition, and we don't actually know how this is going to unfold. So I think ruling things out or ruling things in at this stage is a rather tricky game, in fact. And the production of blue hydrogen wasn't particularly helped by a paper that came out about a year and a half ago, I think it was now, which had a very North American perspective in terms of the efficiencies of blue hydrogen production. And those are not, that's not the sort of operating, those are not the operating parameters that we see here in the UK and in Europe. Where we have much tighter control around things like the potential for methane, fugitive emissions from the process, and also the efficiency of capture of the CO2. So we do know that we can produce low carbon blue hydrogen in a very efficient way. And that will give us the capacity to use it at scale and develop markets, which otherwise we may not be able to easily or readily develop with green hydrogen alone yet.
So can I ask how that's been viewed by the local community, the carbon capture elements, the cluster as a whole? Is it been well received?
I think there's a lot of interest in this. It's fair to say that people are asking questions, and very valid questions too, about how this is going to work, about things like a CO2 pipeline that will be running along the length of the Humber, and a hydrogen pipeline, etc. However, when you take people through the journey of how the Humber has had this long industrial, manufacturing, chemical production, etc. history, they begin to realize actually it's not such a revolution. It's actually more of an evolution of what the Humber area has been doing over many years, many decades, in fact, a century or more. One of our local production facilities at Saltend, now run by the PX group, that's over 100 years old. That's about 105, 106 years old, where we've had this sort of chemical operation and chemical manufacture in our area. So people do recognize the familiarity and the skill and expertise that we have to be able to operate these facilities. That said, people are also concerned about the climate, and they realize we do have to take actions. And so presenting people with the opportunity to actually be on the positive side of a greener economy in our region is one that does appeal.
Thanks, Jonathan. If anyone is interested who's out there listening in our social media platforms, you can go to the Zero Carbon Humber website, and we'll put some links to that. And at this point, I want to say thank you to everyone who has joined us from all around the world, from Diana Gutierrez, all the way from Florida, to other viewers in Mumbai, Manchester, Montreal, and Nigeria. So that's, great to see the reach. One final thing before we move on is something that was raised by a member of our chemical science community, Professor Francis Livins of the University of Manchester, last year in one of our COP26 panels, where he discussed the role of nuclear power to produce hydrogen, and some really fascinating chemistry there about using the heat from reactors for steam electrolysis, or even very high temperature pyrolysis of methane to produce solid carbon hydrogen. And we'll put a link to that recording in our social media also, if you want to find out more about that topic. But yes, thank you, Jonathan, for that overview of the Humber Cluster, introducing us to it. I hope you're able to stay for the rest of the program, and we'll have some video presentations now from the chemical science community, and we'll discuss those and relate those as we go through. So our first clip is from Professor Zhihong Li of Exeter University. She's going to be talking about AEM electrolyzers that use anion exchange membranes to develop hydrogen.
My research group, we are working on anion exchange membrane water electrolyzer. We give the short name AEM, anion exchange membrane. This is before I introduce more about AEM technology, I'd like to share some knowledge in PEM water electrolyzer for comparison. Currently water electrolysis is a green way, effective route to produce hydrogen. And there are three main technology to produce hydrogen from electrolysis. Two methods from room temperature. One is called PEM water electrolyzer. Another is called traditional alkaline water electrolyzer. And there is another method is high temperature solid oxide water electrolyzer. So our research is focused on room temperature water electrolysis, which is AEM water electrolyzer. This technology is an emerging technology just over last decade. On the other hand, PEM water electrolyzer is a matured technology. And currently, people talk about green hydrogen. Most of the hydrogen come from PEM and traditional alkaline water electrolyzer. PEM is developed in 1950s and 60s by GE and NASA. And at that moment, this device is originally proposed to produce oxygen for astronaut life support. And since then, a huge effort put on PEM research and development. Nowadays, it's already commercially available. However, this technology rely on expensive precious metal as a catalyst. So the cost is a big issue because the system rely on precious metals such as platinum, palladium, iridium, ruthenium. So this is the catalyst material used in the device. Why we need this precious metal? Because the system during the operation at the heart of the device, which is we call MEA, membrane electrode assembly, at that interface is a very high acidic environment. So only this type of precious metal are stable under this harsh environment. Also, the system rely on expensive membrane to be operated for the system. What we are doing, we are with the aim to cut the cost. If costs stand high, is meaningless. It's very difficult for practical application. Therefore, we are proposing a novel method to combine the advantage of a PAM system, which is operated at high current and high efficiency, and with the advantage of a traditional alkaline water electrolyzer, which use cheaper non-precious metal as catalyst. So we combine the advantage of these two technologies to develop AEM water electrolyzer. The system operated in alkaline media enable us to use cheaper non-precious metal as a catalyst. Also enable us to use low-cost ion exchange membrane. Therefore, we aiming to achieve cost reduction. So that is our research aim. Specifically, we focus on two areas. One is catalyst development. We select and optimize catalyst material to improve the efficiency, and in the meantime, we focus on cell design. Excellent engineering design is also important to improve the efficiency of the system. Renewable now cost reduction more and more, and the renewable energy become more and more popular. And currently, over 26% of electricity worldwide generated from renewables, which is remarkable. That is the effort, and from many countries and from industry, from academic. That is exactly great example. All the effort together, we can make it happen. In the meantime, I believe if we have similar support from government for hydrogen, we can achieve that goal to reduce cost. Currently, as you know, 96% of hydrogen globally from fossil fuel, only 4% from electrolysis. This electrolysis not from water electrolysis, mainly from as a byproduct from chlor-alkali industry. So we can't rely on fossil fuel, and hydrogen is so important. The big use of hydrogen is for ammonia production as a fertilizer. Actually, over 50% of hydrogen used for ammonia manufacture, and also hydrogen can use for petroleum refinery and for metal and steel production. Also as for hydrogen fuel cell car, electric vehicle. So it's a huge opportunity and application for hydrogen. However, nowadays 96% hydrogen from fossil fuel, from steam methane reform and from gasification. So we must stop it and explore new method, green method towards net zero, and to reduce the consumption fossil fuel.
So that was great to hear about the work on experimental AEM electrolyzers, but of course there are commercial electrolyzers available that use the proton exchange membranes, PEM electrolyzers, and I believe there are a number of those developments planned for the Humber Cluster. Jonathan?
Yes, that's right, John. Actually, there are quite a few projects relying on that technology here in the Humber, at least proposed projects at this stage. So we have a project with our refinery partners, Phillips 66, who are working with Ørsted to supply the low carbon electricity, and with ITM Power, a company based in Sheffield, not that far from the Humber, who are developing this sort of electrolyzer technology along those lines. We also have others in the area. Uniper are also very active in this space, looking at how they can deliver electrolyzer technology into the Humber for the production of green hydrogen too. So there are quite a few different projects looking at using electrolyzer technology to produce green hydrogen.
And we've had a question come here from Dr. Manish Biyani through LinkedIn, who's asking about what the scalable hydrogen technologies are for commercial applications. I think it's interesting that those PEM electrolyzers are modular and scalable. Is that right?
I mean, this is my understanding from the work that ITM Power is the one I know best, who are doing this work here in the Humber, and their whole premise is about trying to emulate the same sort of scalability and efficiencies of scale, shall we say, that we've seen in things like the solar industry, where the more you can actually produce of these modular electrolyzers, the more you can actually scale, develop the scales, the economies of scale rather, to be able to do it in a cheaper and cheaper way, and of course learn by doing as well. And that's exactly what their ITM Power projects are looking to deliver here in the Humber.
Great. Thanks, Jonathan, and thanks to everyone who's watching from around the world. Please do add your questions into the various social media platforms, and we'll try to discuss them as we can. So next up, we've got a video from Dr. Manoj Ravi of the University of Leeds, who's published a review recently in the high-impact journal Chemical Science. If you look online, you should see a QR code where you can download this paper. It's open access and freely available. And the title is Facilitating Green Ammonia Manufacture Under Milder Conditions. What do heterogeneous catalyst formulations have to offer? So I'll let Dr. Ravi talk more about his work.
In the context of our work, we are looking at ammonia, and ammonia has conventionally been looked at as a nitrogen vector in the context of the fertilizer industry, and its current production stands at close to 200 million tons per annum. But going forward, in the context of climate change and green energies, we are looking at ammonia as an energy vector, primarily from a hydrogen perspective. But of course, the manufacture of ammonia, which is already large-scale and widespread all over the world, there needs to be a few tweaks made to that if we have to produce green ammonia and not the conventionally produced brown ammonia in a more economic manner. Now, conventionally, ammonia has been produced from a fossil fuel feedstock to produce hydrogen, which is then combined with nitrogen to produce ammonia. However, in the context of green energies and decarbonization going forward, we should be producing hydrogen from renewable energy sources and then combining it with nitrogen. So this would entail the two different pathways, eventually producing ammonia in a more small scale suited technology, primarily because things like solar energy, wind energy, and all other renewables, they do tend to have intermittencies associated with their supply. So a small scale green ammonia facility, which can then be shipped away to be used either in the fertilizer industry, which is where it is at the moment, or to be used as a hydrogen vector from an energy perspective. The Haber-Bosch process is how ammonia is made. It's a pretty cheap catalyst because it's primarily made of iron. There have been some second generation improvements and also some use of ruthenium, but that's largely on a small scale because of the costs of ruthenium. Now, the Haber-Bosch process works at very high temperatures and pressures, and that is suited to the large-scale ammonia production which is currently being done. But as I alluded to in my earlier response, green ammonia needs to work on a smaller scale, and thereby moving towards lower temperatures and lower pressures than the conventional Haber-Bosch process would be highly beneficial. But this requires newer catalysts because the iron catalysts that are used at the Haber-Bosch process do not work well at lower temperatures and pressures. Consequently, the search for alternatives has been on, and it's been going on for quite a while now. But over the last 5 to 10 years, we've managed to make real progress in terms of expediting nitrogen activation, which tends to be the rate limiting step in the conventional Haber-Bosch process. We've managed to come across multi-site catalysts, which tend to expedite this process and also deal with the hydrogenation of the activated nitrogen species in a more efficient manner, thereby improving the performance of a catalyst at lower pressures and temperatures. So most of these catalysts tend to be transition metal based, primarily because you need a transition metal to activate nitrogen. But there are other compounds like alkali or alkali metal hydrides, which are now being added because they act as good hydrogen or nitrogen resources during the course of the catalysis. But all of these materials also do not have a great water stability. So there are issues going forward which needs to be looked at. And that's why, as I said, I think the long-term stability testing of some of these catalyst materials are extremely important if they would have to eventually be used in a green ammonia catalysis. Firstly, in terms of green ammonia production, so the kind of retrofitting the existing technology, or what changes do you need to make to suit it for smaller scale production, is going to be one of the key challenges, because the economic viability aspect tends to vary when producing ammonia on a larger scale as opposed to on a smaller scale. So can we successfully address those issues is going to be the first question. Industrial people do suggest that there can be an issue with simply the number of electrolyzers, for instance, that you would need to produce green ammonia. So that certainly is a barrier. The second bit, which I've not alluded to because I've largely been restricting the conversation to green ammonia synthesis, is actually once you have green ammonia, how do you crack it and go back to hydrogen and nitrogen? So the decomposition of green ammonia, if you like. So how do you do that? Because again, there might not be large scale technologies which are directly available for that as of now. So that's very much R&D as well. So how you address that part of the technology is potentially another barrier. So with respect to green ammonia, I think there is immense potential purely from those two perspectives. I think because we have two pressing issues. One is the decarbonization of the fertilizer industry, which is such we need. And then there is, of course, that emphasis on green hydrogen, but we're always limited in terms of the energy storage that green hydrogen can give you because of its volumetric density, and that you cannot store and transport green hydrogen a lot easily. So I think green ammonia in that sense, because it covers two bases, will have immense potential. There is the decarbonization perspective from a food perspective, but also sustainable energy. So there is immense potential definitely for green ammonia going forward on both those lines.
So, Jonathan, Dr. Munoj Ravi there is talking about green ammonia production from electrolyzers at small scale, but currently our ammonia production is very, very large scale, isn't it, and very concentrated. I believe that there is a fertilizer plant at Teesside that's linked through the East Coast cluster to the Humber cluster development, and that there's been disruptions there that's been making it to the news.
Yes, this is true, John. In fact, I mean, there have been two big fertilizer production plants in the UK until recently owned by CF Industries, one over in the northwest at Ince, which I think shut either earlier this year or last year. And more recently, of course, we've seen the impact of some questions around the high gas price and the economics of CF's plant up at Billingham on Teesside, which, as you say, is connected to the Humber in a variety of different ways, but principally through the East Coast cluster as well. So, these are important manufacturing facilities, and what we face is the challenge, I guess, of managing our way through to a net zero transition, where we also are still able to do that in some sort of a sufficiently economic way, so that companies who want to operate facilities and do it in a sustainable manner, but also one in which we are able to have access to the same sorts of goods and services that we need. In this case, of course, we're talking about things like fertilizer production, which all of our farmers will be looking to access for food production, but also from the point of view of things like CO2. And we have a certain irony here where, we're talking a lot about CO2 as far as the climate goes, and trying to remove or reduce that from various production operations. But here is a classic example of where CO2 actually is a feedstock and is used in other processes. So whether that's to gasify your beverages, beer, soft drinks, etc., or whether that's for medical reasons, or whether it's in the slaughter industries to stun animals before they are killed, or indeed in nuclear reactors where it can be used as a coolant gas. So these are all vital applications, and so we do need to think about where we can source CO2 from. And I know a lot of work has been done behind the scenes to assure businesses that the access they need to CO2 in the UK can still be provided, as well as the fertilizer for farmers. But it just indicates that all of these different aspects are there are many different jigsaw piece puzzles to make up these sorts of chemical process conundrums, shall we say.
Yes, all knitted together and illustrating lots of different aspects of chemistry. If we've got any teachers and educators in our audience today, can I point them towards our resources for teaching around ammonia, including reference to those news articles you mentioned about the CO2 shortage in the UK. There'll be links to those on our social media. We'll move on to discuss a different topic, but one that's no less fascinating. Louise Oldham of Imperial College London is a postgraduate researcher in the James Durrant Group, and she's working on photocatalysis, and she'll tell us.
I guess as a principle, it's quite a similar setup. So it's still two electrodes, and we've still got two half reactions, one doing oxidation and one doing reduction. But whereas in electrolysis, you've got a bias driving that process. In electrolysis or photoelectrochemistry, you also have the addition of light. So one or both electrodes are made of semiconductors, which when they absorb like incoming solar light, you get photoexcited charges, and those charges can directly participate in the half reactions. So this therefore means that you don't need as much external bias applied. I think there are some systems where you don't need bias at all. But the chemistry, I guess, setup is quite similar. By having the excited charges directly from sunlight, it means that you need far less external energy applied in order to achieve the same reactions. The reduction of protons to hydrogen obviously makes hydrogen fuel, which is great. Another thing that people are looking at is the reduction of CO2 to then make hydrocarbon-based fuels, and obviously potentially has the added benefit of being a way of using up some of the CO2 we've already emitted out. So the work I actually do looks at the other side of the other half reaction, which in the case of water splitting is the oxygen evolution side. The reason the focus is there is that half reaction is widely understood to be the sort of energetically limiting part of the whole process. So it's really important that we try and understand that bottleneck in order to make the whole process more commercially viable, essentially. But actually the oxidation of water to oxygen is quite challenging. And so there's quite a lot of work at the moment in potentially coupling, you still got your hydrogen production on the cathode side, but at the anode, instead of oxidizing water, potentially oxidizing small organic molecules. And these could be waste products from industry. So a big one that people are looking at the moment, for example, is glycerol, which is a key waste product from the biodiesel industry. And if you oxidize it to higher value products on the anode side, you can then make use of the anode product as well as the cathode product, which is potentially another step in getting the whole system to a commercial stage sooner, and has the added benefit of being energetically simpler potentially as well. The work that I do, or that we do in our group generally, is looking at trying to understand how these materials work on quite a very small scale, so on the charge carrier level, trying to understand what's happening inside the material. And the sort of long-term aim of those sorts of studies is to then sort of think about how you rationally design materials to better improve the performance, the efficiency. Unfortunately, like steam reforming of methane to make hydrogen is still the cheapest way by far of making hydrogen. And we do live in a capitalist society, so money is important. It's important that you can make the hydrogen cheaply if it's going to be competitive. So we need to have efficient systems that can carry out this reaction in a way that then makes them cost competitive. And that also means that we need to be looking at utilizing cheap materials as well. So some of the best performing materials aren't necessarily the most abundant or the easiest to access, or might come with other sort of ethical implications. So it's important to understand why things work, and then we can start making other choices about alternatives or how to build more complex systems. Generally, the most promising materials for photoanodes are metal oxide based, and that's largely because they have quite good stability in aqueous environments. They are generally quite resistant to photocorrosion and also quite abundant. And some of the key ones that have been studied so far in the field are things like tungsten oxide, titanium dioxide, and hematite. And most of my work at the moment has focused on bismuth vanadate, which is one of the highest performing in the field.
So Jonathan, I think that that's a really fascinating bit of work, because it forces us to think that hydrogen is just one of a potential range of solar fuels and feedstocks, and that there's really kind of great opportunities in looking to produce other molecules that can be a valuable fuel, or can go on to have another value elsewhere in our industrial system, and that might also help us to reduce the amount of infrastructure we need if we can go directly from those photocatalytic reactors to producing something that can be used directly as a solar fuel.
Absolutely right. I mean, it does offer some tremendous advantages, like any such technology or tool, as it were, in the energy transition toolbox. It also has its drawbacks, and you know, it's a relatively novel technology in terms of its deployability. But if we can overcome and start to think about the modularity of how we can deploy it and where we can deploy it, then there could well be some a role for photocatalysis to play in terms of that in that space, John. Absolutely, yeah.
Yes, so we're using sunlight not just to produce electricity, but to produce direct molecular stores of energy that miss out all of the or reduce the requirement for transmission, distribution, and storage infrastructures that are very material intensive. If anyone listening is interested in understanding some of the issues around where we source these precious elements, these valuable minerals and materials, the RSC has been working on a campaign in this area for a number of years. That's the Precious Elements campaign, to encourage people to recycle their waste electronics and to understand more about the resources that go into batteries and in other new low carbon technologies. And so we'll put a link to that in our social media as well if you want to find out more. And again, potential educators could use that in their classrooms, as we've seen a bit of interest on the social media comments below there as well. So thanks for that. Jonathan, one other thing that just occurred to me is that if we're thinking about storage, it doesn't have to be in complex molecules, does it? You can store hydrogen as a gas, and I believe that that's something that's available on the east coast of the UK.
Absolutely. So we've got two significant gas storage reservoirs here in the Humber. There's one that's quite well known, I think, because it's been in the news over the last 4 or 5 years, which is the Rough Gas Storage Facility run by Centrica Storage. But we also have the Aldborough Gas Storage Caverns just at the coast, in fact, which are run by SSE. And both of those storage facilities effectively allow us to investigate and repurpose those storage facilities. Rather than storing methane, we could potentially store hydrogen there. And that gives us the opportunity to think about how we manage our way through, for instance, if we think about photocatalysis options. That's fantastic when we have access to sufficient solar radiation. Low carbon wind energy is great when we have access to sufficient wind, but there are times when those sorts of weather features aren't available to us, and therefore we also need to think about what our backup options might be, and hydrogen storage could certainly well come into play. In fact, we've calculated that in our region, those two gas storage facilities, we have enough hydrogen to power effectively 2 million homes for an entire year, just with the hydrogen that would be stored in those facilities. That's
a very substantial scale. So as we think about scale, let's move to some of the largest hydrogen projects in the world. We're going to hear now from Huyen Din at the National Renewable Energy Laboratory in the USA. She's the director of their Hydrogen project.
The one that's more basic science is the lowest TRL level would be the Stitch water spring technology, that's solar thermochemical. We're still in the materials discovery stage for this technology, and hence there's a lot of theory guided work. So we're trying to understand what type of metal oxide materials, perovskite materials, classes that what properties they have to be able to split water at these high temperatures. And so we rely on theory and machine learning at this stage to screen materials for various different properties and figure out what are the key metrics and properties of those materials that will lead to water splitting. The next one would be PC. We're we're still working on materials development. The materials that we focus on has been semiconductor, thin film semiconductor materials, like 3,5 materials that have demonstrated high solar to hydrogen efficiency, but its durability is very poor and it is very expensive. And so within hydrogen currently, our research is focused on enhancing that durability. The next level would be both high and low temperature electrolysis. They are closer, I wouldn't say to commercialization, but they are higher up in the TRL scale. Within hydrogen, we focus on alkaline exchange membrane electrolysis rather than proton exchange membrane or polymer electrolyte membrane electrolysis, because it is a lower TRL technology, and there's a lot of materials development that still needs to be done. We don't currently have a stable, durable membrane for this technology, and that's the key that we're working on, right? And the catalyst to work with it to bring it up to the type of performance and durability that PEM electrolysis currently have. Within the high temperature electrolysis, we're working on proton conducting SOEC. That's all electrolyzers. And that's lower in TRL than the oxygen conducting SOEC. And again, the electrolyte is still very new, and it's not stable. It has a current leakage issue. And within hydrogen, that's what we focus on, is understanding what those, why these electrolytes, solid electrolytes in the protonic form that exchange protons are leaking and not highly conductive, and how do we improve that with theory and experiment. The new consortium is a 10 national lab consortium. It's very big. It comprised of the higher TRL technologies that I was referring to, alluding to earlier, and that's the PEM electrolysis and the solid oxide electrolysis. Because they are closer to commercialization, there are some commercial PEM electrolyzers already, but they are expensive, and they were over-designed for the application. And so with the hydrogen shot within the Department of Energy that's set for us here, for trying to achieve $1 per kilogram of hydrogen within 1 decade, 111, that's why this consortium was built, is trying to really leverage the material sets that are available currently and work, and try to optimize it by integrating together the catalyst, the membrane, the gas diffusion layer, the porous transfer layer, and all of that, to maximize, right, the performance, the durability, and to lower the cost. So bring down the catalyst loading, as minimal as possible, but still able to perform and have a long durability. All three simultaneously is difficult to achieve, right? You can do one or the other, but that's difficult to do that. So the consortium comprised of two kind of subgroups. One is focused on the low PEM electrolysis side, and the other one focuses on the oxygen conducting SOEC. And for them also, it's about optimization of the materials that's currently there. There's no material development work at this time, but they may be in the future. And really trying to understand the integration of this and of the material sets, and how to achieve the performance and the low cost and durability. So those are the ones that we see are closer to commercialization, and that's why there's a lot of effort in trying to work together as a consortium to bring that technology forward to commercialization for the applications that we need, right? Beyond just feeding it hydrogen to fuel cells. I've been working on this for several decades now, fuel cells and hydrogen production, and it's always been incremental funding. And so we can only do incremental research and progress. It's so great to see the government, the federal government, stepping in now and providing billions of dollars in funding for the hydrogen hubs, 8 billion to be specific, for hydrogen hubs across the U.S., and then 1 billion for electrolysis R&D, and then $500 million for manufacturing. These are unprecedented type of funding and effort that the federal government is putting in, and then engaging, the industry partners, the academics to do that. So there's the deployment and demonstration part of it that we really need to see how all these technologies integrate together, right? Not just to make hydrogen, but its application end use. So all this will be in one place. And the integration part is key to really see how we can do that with all the different technologies that are out there, and what the application can be used for, and how it can impact the communities that are nearby. I'm so excited about that. And I just attended the Hydrogen Online conference that was 24 hours. That was exciting to see how all the different countries around the world are engaging in this work and showing all the different demonstrations they have and deployment work in hydrogen that they have currently, and how excited they all are. So I am excited, and seeing that people around the world are working together to bring this happen, because I think it could be very impactful on the environment, bringing down the carbon emission. So yes, I think focusing on R&D is things that we still need to do, and doing it quicker by working together, and doing deployment and demonstration to really help de-risk the commercialization of this technology.
So that's really heartening, Jonathan, hearing about the international perspective and the scale of some of the things that Huyen was mentioning there. That US program, the hydrogen shot, to get $1 per kilogram within a decade is really quite something. I mean, that's an 80% reduction from where we are now. And last week we heard at COP27 that the African and Middle Eastern nations were positioning themselves to become big exporters of hydrogen. Do you think there's something in that for the UK?
Yeah, I mean, you're right that the scale and ambition that they're setting in the US is hugely important. But don't forget, of course, we've got our own 10 gigawatt target here in the UK for hydrogen too. Yeah, in terms of the export opportunities for other countries around the world that might be blessed with, for example, a lot of solar radiation or a lot of wind power, for example, then those are useful opportunities for them to potentially serve as an energy hub, providing energy rather to other parts of the world, whether they provide it directly in the form of hydrogen, which is a lot more challenging to transport, or whether they provide it in the form of something like ammonia, which is a little bit easier to transport, but still obviously has an energy and economic cost to doing so. I mean, by far and away, obviously the best thing to do in many regards is to consume and use your hydrogen where you actually produce it, and then you avoid some of these particular issues. But like most things in life, and certainly the energy transition, there is never a clear black and white answer to some of these particular questions, John.
Great, thanks, Jonathan. And so finally, I'm pleased to say that we have the associate editor of our journal EES Catalysis, Professor Zhishan Zhu of Nanyang Technological University in Singapore. And he's going to be talking about his own electrocatalytic research and the journal that is just launching. So here he is now.
My research is mainly about electrocatalysis, and actually I have a focus on the hydrogen, especially on the green hydrogen. So if I show you the slides, and I can show you that actually one of the focus of research is the green hydrogen. That says, like, if we use the sustainable energy resource to supply, let's say, the power we need to split the water, and then we can produce the green hydrogen. So that actually involves the water splitting reaction we call the hydrogen electrolysis. So although this process
And the product we want is hydrogen because we're going to store the electricity in the hydrogen molecule. But the major energy loss actually is at the anode, the oxygen side. So that in our group, actually, we put a lot of effort on this anode side. That's we working on the oxygen evolution reaction. We looking for the better catalyst. We're looking for the better understanding of the catalyst, the mechanism, etc. So, for example, in early years, we firstly reviewed geometry effect in the spinel oxides, which is kind of a catalyst to catalyze and the oxygen evolution reaction and also the oxygen reduction reaction. So we find actually the octahedra coordinated the transition metals will be more dominant to determine the activity. And of course, we also investigate using some in situ characterization tools to observe, let's say, to investigate the surface change during this kind of the OER reaction, because reaction condition actually is very tough. So nearly all materials can transform their surface or at least change the surface phase under that kind of condition. And also we look at other bulk chemistry, including the spinel and the perovskite, etc. And for example, the iridium-based perovskite oxides, which have surface retransformation to give us a stable iridium surface, and which have a high activity for the OER in the acid. And we are also looking for alternative reactions to the OER. For example, if we find some other small molecules which can be oxidized at the anode, but at a lower potential. That means theoretically, or let's say thermodynamically, we are able to lower the cell voltage. In this case, we can save the electricity used for this hydrogen production. And also we can, if the small molecules is a kind of a cheaper molecule, and then we can get a value added, a new product from the anode. And that means we can even lower the cost, or let's say to bring additional value to this process. We can call that cogeneration. And also in recent years, we are quite interested in the kind of magnetic effect on this OER reaction. For example, we often talk about kind of potentially we talk about the spin effect, because the oxygen is a triplet oxygen. And theoretically, they may have kind of a spin selective electron transfer in this reaction. But of course, in this field, there is a big argument if this is really a matter in this OER field. So in this case, when we do the measurement, when we apply the external magnetic field on the electrode, we must be very careful, because the circuit will have a change in the magnetic flux. And then that will cause some bias, induce the current or something. And so sometimes we observed the enhancement probably comes from something else, right? Including the conductivity change or the mass transportation improvement or something. So that's so the measurement should be really careful on that. And also we can find something like, for example, ferromagnetic material. We can find at which condition they will have improvement, at which condition they won't have improvement. Right? So this is something we are quite interested. So the more details about our research actually can find in our research group. If you scan this code, and actually you can reach my the white page of my research group. Right? So now let's talk about a little bit the journal of the EES Catalysis. So I'm now serving as an associate editor for this journal. And this is kind of a new journal from the environmental and energy science, right? But this is kind of a go open access. So we actually look for the exceptional research on the energy and the environmental catalysis, and it's open to everyone. It's free at this moment. It's free to publish, and of course, for the lifetime, that's free to read and impactful for all this concept, this journal. So on behalf of the editor-in-chief, the Professor Shizhang Qiao, we welcome your submission, and also we hope you had the attention on this new journal, and we hope that can deliver the same impact and influence as associated with energy and environmental science. And we publish and transdisciplinary research across the chemistry and materials science and engineering. And again, we welcome your attention and to your submission, and of course, as a reader to this journal. Of course, I think it is quite important. I mean, that's important globally. And it's not just for a few countries. That's for all the human being. I mean, we're looking for the kind of a sustainable solutions. I mean, these kind of it's a pity if we just burn a fossil fuel, because that's a precious chemical resource. For example, we use them for polymer. We make it a polymer. Even for the methane or something. That's really precious resource. We should not burn them. So that means we are really looking for the alternative and clean and sustainable way to supply to support our development of economy and society. So definitely hydrogen is very promising one. But I think the K is not just catalyst, the development, not just the materials development, but also at the device level, we need more investment, integration issues, the smart design, and also the cost saving for the systems.
So that's great to hear from Professor Zhu, and it's striking to me as I've kind of rewatched all of these videos, is spotting that link between his work and Professor Lee's work and Louise Oldham's work, where they're trying to do some value adding in the chemistry. So they're working on hydrogen production, but also looking at the other side of the electrolyzer with a view to other chemicals and integrated chemical production, which reminds me of the Humber Cluster again, Jonathan, about all of those different projects that are connected.
It's a great point, John, and this is why the CBI have developed the concept of the Humber Cluster. It's the first time they've made this move from advocacy to action, and really the CBI is not in here to bat for one particular business or one particular company, rather. It's about actually being seen to take a sort of agnostic position around the technologies or the companies and say, no, this is just businesses coming together around the Humber and working with the public sector too, to be able to help decarbonize and get our industry in the Humber to net zero, and using our convening power to do that.
That's super. Well, thank you, Jonathan. Thanks for joining us for this live session. It's been great to have you with me. And thank you also to our contributors, Xiaohong Li, Manoj Ravi, Louise Oldham, Huyen Din, Xishuan Xu, and of course you again, Jonathan. So finally, I mentioned earlier that we have a hydrogen-themed special collection of our journal articles being released today. It's a fantastic resource which has 45 articles from our scientific journals, and they're all freely available to download on the topics that we've discussed today, and many more that we didn't have time. So you'll find articles on formic acid as a hydrogen carrier, comparable to ammonia, with data-driven screening protocols for catalytic materials, and further on to looking at life cycle and techno-economic assessments of different pathways in the round. So this collection is a mixture of reviews and the latest research, and I really encourage you to check it out by following the QR code or the links in the social media. If you've enjoyed this session, on Thursday the 17th of November, you'll find the final broadcast in our series, which is the RSC Sustainable Food Technology and COP27 event. It'll be back here on YouTube, LinkedIn and Twitter channels, also at 1 p.m, where we'll have speakers from around the world. And finally, make sure you subscribe and follow us on social media for more on our sustainability work, and listen to our Brought to You by Chemistry podcast, with recent series covering big issues in plastics and batteries that are told through engaging and captivating stories. Once again, thank you for joining me. Thank you to our guests and speakers. Have a great day, and we'll see you in our next live session.